Hi class, welcome to Research Methods. I'm Dr. Shantz, and our video today is looking at Chapter 13, Inferential Statistics. For a quick overview, we're going to talk a lot about null hypothesis significance testing, look at some basic tests, the usefulness of effect sizes and confidence intervals, and work with some frequently asked questions that I tend to get from this chapter. So from your Elements of Statistics class, or back in the day, you probably were introduced to a process similar to this one, where you would need to state the null and alternative hypotheses, determine your level of risk or the alpha level for a test, select the appropriate test statistic, calculate the test or the test estimate, determine the critical value and compare the obtained value to the critical value on like a table in the back of the book, something like that, and then decide that if the obtained or estimate exceeds the critical value, you would reject the null, and if the obtained value did not exceed the critical value, then you would retain the null. So for what we're going into today, some things we have the program do for us. We have either SPSS or JASP or R, whatever statistical program we're using. It's going to do things like calculate the test statistic, determine the critical value, and compare the estimate to the critical value. It's even going to give us a little indicator like an asterisk if the test estimate is significant, or we just look at the p-value and we're looking for a p-value less than 0.05 to indicate that the test estimate exceeded the critical value. So we approach it a little differently when we're using a statistical program to run the calculations instead of us doing it paper, pencil, and looking up tables. Another thing to note is this level of risk, alpha. In psychology, we pretty much always use an alpha of 0.05. So any value, any p-value less than 0.05 is significant. So what we need to look at today is stating the null and alternative hypotheses and selecting the appropriate test statistic. So we'll consider by looking at these different inferential tests that are coupled with which test should be run. Which test should be run depends on the research question. Is the research question talking about a relationship between variables or looking at differences between groups? We'll consider how null and alternative hypotheses are made for these two different types. We'll look at the correlation coefficient, which is relationship between variables, and we'll look at a t-test between independent samples, which is differences between two independent groups. Both of these are null hypotheses, but for two different types of tests. What I want you to keep in mind with the null hypothesis is that null means nothing. It means there's no difference, there's no relationship, nothing, nada, nadie, ninguno, nothing. So when we're talking about differences between groups, we're saying there's no difference between these two groups. When we're talking a relationship between variables, the correlation, we're saying there's no relationship between those two variables. So keep in mind, null means nothing. Another thing I want to point out here is the Greek letters. This one's called mu, and this one's called rho. When we're looking at the null hypothesis, typically we're making a statement about the whole population. So mu is the population mean. The average for males, all the males in the population, is equal to the average of the population of females. There's no difference between them because they're equal to each other. That's your difference between groups. Here, the relationship between two variables, rho means the relationship in the population. The relationship between x and y is 0. Again, null means there's no relationship there. And if you remember our correlation, when the correlation coefficient was 0, it meant there's no relationship. So this makes sense that there's no relationship when we're talking correlation, or if we're talking about a test between groups, like differences between groups, the null is saying there is no difference between them. They are equal. The alternative hypothesis does not use population parameters in the Greek letters. It uses sample statistics like letters instead of Greek letters because it's only talking about the sample. The alternative hypothesis of the sample is saying the average value for males is not equal to the average value for females. So this is comparing two groups. It's saying that the alternative to the null, remember the null said there is no difference. The alternative says there is a significant difference. Here on the correlation test, the correlation coefficient is the test for correlation. So the correlation coefficient between these two variables, x and y, is not equal to 0. So back at our null, we said the relationship is 0, so there's no relationship being 0. Whereas the alternative is saying the relationship is not 0. In other words, there is a significant relationship between x and y. So this one's our correlation. This one would be an independent t-test, the alternative hypothesis. So it goes back to determining the appropriate test to use to be able to know if you're creating your null and alternative hypothesis as a differences between groups set or a correlation, relationships between variables set, because it's not going to be both. It'll be one or the other. And I know that looking at the null and alternative for two different types of tests can be confusing, but we needed to have that information before moving on to the example. So which test should be conducted? It depends on if we're looking at a relationship between variables or we're looking at differences between groups. And that tells us which path we're going on at the beginning. So let's try it out. Suppose we developed a new program to increase problem-solving skills of children, and we want to know if the program works. And the way we're going to assess this is by having some children in a control group, so they don't get exposure to the new program, the new training program, and children in an experimental group. So what type of test would be appropriate here? Would we be looking at the differences between groups, like a t-test, or the correlation between between variables? Yep, we want differences between groups here because we have a control group and we have an experimental group. So our next step is to state the null and alternative hypothesis. And we want some tips on how to do that. Some tips to use when creating your hypothesis statements. You want it to be declarative, as in a statement. This isn't the research question. You're saying what we're testing. You're testing either there is a relationship between variables or there is a difference between groups, and you say it. You also want to say what you're expecting. Are you expecting one group to be higher or lower in a score than the other group? Are you expecting a relationship between variables to be positive or negative? You also want your hypothesis to be consistent with prior theory and research. That's why the research instructor or the researcher has to look at the literature first and see what has been done before, what theories might inform that research question and the hypotheses. And the hypothesis statements have to be brief and testable. It's really good to use the if-then statement when you're trying to say if a group had the training, then they would have higher scores. Using this guidance, you should be able to create an alternative hypothesis to help answer a research question. So now let's try out our example. In this case, our study prediction, which we call the alternative hypothesis, is that the groups will be different. In fact, we expect the experimental group children will have higher problem-solving skills than the control group children. The null hypothesis would be, again, nothing, that there is no difference between those two groups. So pause the video here and try it out before moving to the next slide. Write out both the formula and your statement that would go with the null hypothesis and the alternative hypothesis. Write it out, and it also helps to say it. That's kind of the trick of getting these down and understanding your null hypothesis compared to your alternative hypothesis. So here's our null hypothesis. Again, the null means nothing. That there is no difference in what? The dependent variable, the problem-solving skills. No difference in problem-solving skills between group 1, the control group, and group 2, the experimental group. Now what about the alternative hypothesis? Which one of these would be correct for our example? So we have that the control group will not be the same as the experimental group. We have the control group will be greater than the experimental group. And we have the control group will be less than the experimental group. Any of these would be viable alternative hypotheses because none of them say that they're equal, right? But which one is correct for the hypotheses that we're testing? This comes down to looking at a directional versus a non-directional hypothesis. And what do I mean by that? Well, a non-directional hypothesis does not say that one's going to be greater than the other. It would just say they're going to be different, right? Not that one's higher, one's lower. It's just those two groups are different, are significantly different from each other, without saying exactly what the difference is. And when you have a non-directional hypothesis, it's being tested with a two-tailed test. That means that 0.5, that p less than 0.05, that critical value space, is split up between both sides. The test estimate could be in this little tail or this little tail to be considered significant test estimate. But anywhere in the middle would mean that it's not a significant test estimate. And that's if we were saying the average for the experimental group is significantly different than the average for the control group. Again, not saying which one's going to be higher or lower. If you were running a correlation test, you have the same situation that it could be a non-directional hypothesis. And that's when you're saying that there is a significant relationship between those variables, but you're not saying if it's positive or negative. You're not giving a direction to it. So that would be a non-directional alternative hypothesis, which uses a two-tailed test. With a directional alternative hypothesis, you're choosing which way you think the groups are going to be different, or which way you think the correlation is going to be direction, like if it's going to be positive or negative. For our example, we were looking between groups. And it would be like saying the average for the experimental group is significantly greater than the average for the control group. And that 0.05 is all on one side, one tail. And that's why it's called a one-tailed test. So when we have a directional hypothesis, we're using a one-tailed test and we're stating in that alternative hypothesis which direction we think it's going to go, which group is going to have a higher score, or which direction is it positive or negative if it was a correlation test. So both your t-tests and your correlation test could be non-directional or directional, depending on your research question and the hypothesis statement you're making. So what about our hypothesis, our example? We already have our null. There's no difference in average scores between the control and experimental conditions. And our study prediction is that the groups will differ, with the experimental group having higher problem-solving skills than the control group. And that indicates a directional hypothesis. Which one is it? The last one. There is a difference between control and experimental conditions, such that the control group will have a lower average scores compared to the average of experimental group. So, now that we've talked through some null and alternative hypotheses generation, let's look at the different basic tests that we're going to be working with. We're going to start with the correlation because we've already done correlation. And then we're going to look at some t-tests, and we will finish up talking about some ANOVAs, or analysis of variance. Since we've already discussed about correlations, this is somewhat of a recap. The correlation quantifies a linear relationship between variables. We use a scatter plot to visualize it. The Pearson's correlation coefficient, R, is used to indicate the magnitude and direction of the correlation, and it ranges from -1 to +1. And the effect size, R squared, or the coefficient of determination, is just the Pearson correlation coefficient squared. And it indicates the percent of shared variation between those two variables. Moving on to our t-tests and ANOVAs, we have lots of different types here. Now keep in mind that t-tests and ANOVAs always are looking at the average scores, the differences between them, between groups or occurrences. Now the t-tests are always about two. They're looking at differences between two groups, two occurrences, two things, right? As soon as you get above 2, you're no longer doing a t-test. Our examples here. For the first example, it's called a one-sample t-test. And it's when you're looking at your sample compared to the population. So it means that you have to know the average of the population to be able to run a one-sample t-test. It would be like comparing students' perceptions of research methods from UWF to a known average of all the students in the nation, their perceptions of research methods. So you got to know what that score is for the population and compare it to your sample group. Example number 2 is looking at two independent groups. So they're both part of the sample, but in two conditions. That would be like perceptions of research methods for students who plan to go to grad school compared to the perceptions of research methods for the students who plan to get an applied job. In example number 3, the paired samples or dependent samples t-test means that you have two occurrences or some kind of relationship between the two scores. For example, you could have a pre-test, post-test, where you test students at the beginning of the term and then test them again with the same test at the end of the term to see if the scores are significantly different. It would be like comparing students' perceptions of research methods at the beginning of the term compared to their perceptions at the end of the term. Now, across all these t-tests, I want you to think about how are they different and how are they the same? Once we get into more than two groups or more than two occurrences, we're talking about ANOVAs, analysis of variance. Now, a one-way ANOVA would be comparing between more than two groups. So we had talked about how the research methods instructor had three classes, an early morning, a mid-morning, and an afternoon, right? And those are three separate groups. No one's in two classes. So he could find out if there are differences in perceptions of research methods across those three classes. Now going into your two-way ANOVA, which would also be called a factorial ANOVA, would be comparing within groups as well. That would be like if we had the research methods instructor with his three classes and their plans for after graduation, going to a graduate school or acquiring an applied position. And that would be called a 3 by 2 because you have one variable with three options, three conditions, and another variable with two conditions. So what did these tests look like statistically? Well, a null hypothesis is going to say that the difference between these two groups is 0. So it would be almost like these two curves are right on top of each other because their average there at the top is the same, is so much the same it's not significantly different. Whereas the alternative hypothesis is saying that this difference between the average here and the average here, the two groups, is significantly different. Now, graphically, we communicate differences between groups using a box plot. Here is a box plot of GPA, that's the outcome variable, the dependent variable, by gender, male and female. So these are two independent groups, and looking at the average, which is that dark line in the middle, that's the mean for female, the mean for male of GPA on those two independent groups. That's what we would use to illustrate the differences between groups. Now, similarly, looking at ANOVA variance or analysis, ANOVAs, this starts getting a little more complicated because now we're comparing between the variation within a group and the variation between groups. Because remember, this is no longer between two groups. This is more than two groups. So if you had three groups, the ANOVA looks at the variation within a group compared to the variation between. Now, generally, between group variation is due to the treatment, due to whatever experiment, manipulated IV is going on, like a treatment, a training, or whatever other condition is going on. And the within group variance is due to just individual differences, and it's just considered error. So this is estimated with an F test, which we're not going to be running in RM1. If you want to get into F tests, you're going to have to take RM2. Still, graphically, we would look at this using a box plot. So if we had GPA, again, as the outcome variable, and our three groups, independent groups, are major, computer science majors, engineering majors, and other sciences. And there's the mean, the dark line in the middle. We can see that they're different, but we don't know if they're significantly different unless we run the test for it and find out if the differences between groups is significantly different. Okay, so that's it for our basic tests. I did want to come back around to reporting results. When reporting results, we already know to tell the reader which test was being conducted, which variables were involved, the stats line, which is going to be the test estimate, the p-value, and I also mentioned that you're going to be reporting effect size or confidence interval. Now, why is that? Well, just because an estimate is significant does not mean that it's impactful. Like, it goes into the conversation about the practical versus statistical significance. Just because we have a test estimate that's less than p05 does not mean that it has an impact in the world. So one way we quantify that is with effect size. Our typical effect sizes, we use Cohen's d for looking at effect size for between groups, so for your t-tests. And we use the coefficient of determination, or the Pearson's R squared, for our effect size for correlations. Now, with confidence intervals, think towards our sampling error conversation. So sampling error means that if I draw a sample from the population and I get the average for the sample and compare it to the population average, they're going to be a little different. Or if I drew a bunch of samples and I took the average in each of those samples on any specific variable, they're going to be somewhat a little different, each group of sample, right? And those differences are considered sampling error. It could happen that due to the sample not being exactly like the population, that I could find a significant effect only being true for the sample and not really the population, right? Type 1 error. And that's why the test statistic estimate is not 100% guaranteed. Now, wouldn't it be nice to know precisely how accurate the estimate is? In other words, how precise is this estimate? Well, the confidence interval gives us a way to know how accurate that test estimate is. Let's take a look at these. This is a 95% confidence interval of a test estimate. So the estimate itself would have occurred someplace in the middle. And you see that the range from the lower value to the higher value is 0.55 to 1.23. So it's a little less than like 1, but it's positive. We have a positive 5.5 and a positive 1.23. So that is a significant test estimate, and it's that accurate. It's almost like if I was trying to guess someone's age, and I said, oh, this person looks around 30 years old, give or take 10 years. Where I'm saying they could be anywhere from 20 to 40 years old, that's a big gap, right? But if I said, oh, this person is around 30 years old, give or take a year, well, then I'm saying 29 to 31, I'm pretty accurate, right? I'm pretty sure about my estimate. It's the same thing here with these confidence intervals. When you see a skinny, really tight confidence interval, then that test estimate is pretty sure of that estimate. It's pretty right on. But if you see a really large, from the lower to the higher, see this is 0.12 to 727, that is not very sure. It could be anywhere, right? So that's one way to tell how accurate or how precise is the estimation of that test estimate, is by looking at the confidence interval. And then I wanted to show you this one. Remember how the null hypothesis is 0, right? That there's no difference or there's 0 relationship between the variables, right? So if a test estimate could have been 0, then you would have supported the null hypothesis, right? Anytime you see a confidence interval that is on both sides, like I have a negative number and a positive number, and 0 would have occurred between the lower and upper bound there, then I know that that test estimate is not significant, because it could have been 0, and 0 means the null was the correct decision to stay with there. So just some tips on reading confidence intervals. Statistically, if we were calculating confidence intervals by hand, it would go like this. We would take the test estimate and we would add 1.96 times the standard deviation, and we'd also subtract 1.96 times the standard deviation. And those would give us the upper and lower bounds for that 95% confidence interval. If we wanted a bigger confidence interval, like 99% sure of what the estimate was, we would multiply by 2 standard deviations, the 2.56. Now, we're going to use stats software. We are not calculating confidence interval by hand. We will use JASP, SPSS, R, or some software to tell us what the confidence intervals are when we need them. Okay, so I just had a few frequently asked questions that would come up about this chapter. One having to do with the talk about, okay, how do we know sample size and power and the role of sample size in estimating that test statistic? Well, it's going to depend on the size of the effect that you're looking for. Like if you're looking for a really small effect, it would take a larger sample to identify it. If the effect you're looking for is really huge already, it won't take as much sample. So how do you know the size of the effect you're looking for, or how do researchers know? Well, they got to do their literature review. They got to read the theory, know what relationships they're looking for, see what's already been done in the literature to see what effect size they should be looking for. That's how they know the effect size of what they're after. But then power, they have to have enough power to detect that effect size. And that's going to have to do with the risk level they're willing to take. And as we said, psychology, we typically use a risk level of 5, 0.05, a 5% chance of making a type 1 error. And the sample size. The smaller effect you're looking for, the bigger sample size you need. Now, how do researchers know the sample size they're going to need? Well, they can do what's called a power test. And a power test is when you use an application and you say what size effect you're looking for and what type of test you're going to use. And it can determine the sample size that you need to identify that level of effect in a sample. Now, in your book, they did a example. It's not a priori. In other words, it wasn't finding out how much sample size they needed. It was looking at after the fact or post hoc, how much power did that test have? So they said that they had a test, a correlation test, so that's something you need, of plus 0.3, and they had a sample size of 50. And they used that information to find out how much power the test had. So what they did here, they did something like G-Power, an application, to determine how much power the test had after the fact. They put in that it was a correlation. It's a post hoc. In other words, they already have the alpha and sample size and the effect size. So the alpha, 0.05, the sample size was 50, and their power was 0.59 right there. That's how they got to that. And while it's not in the scope of what we do in undergrad research methods class, that's how they found that number. And they do give you a link to G-Power, but Again, you would have to know the effect size you're looking for and what test you wanted to conduct to be able to find out the sample size you need. So one reason I wanted to bring this up is that a question that I've had is how do you know what sample size you need, and why do researchers not just have that much sample? And you'll see it in limitations of the study. When you're reading a study and it talks about the limitations, we didn't have enough sample size. That means that either the researchers did not conduct a power test, or they didn't really know the effect size they needed, or they didn't know what tests they were going to conduct. So they needed to do more literature review and more developing their hypothesis. Or they had the power test results, but they just were not able to acquire an adequate sample size. In other words, they put out their notices, they tried to recruit enough sample, but they didn't get enough people to participate in the study. Okay. And the last question I get is about type 1 and type 2 error, and they're also called false positive and false negatives. A type 1 error is when there really is no effect in the population. So the null hypothesis really is true. But in my sample, I rejected the null because I had a significant test estimate. So I had that error because my sample produced a significant test estimate that was not really true in the population. That's a type 1 error. Type 2 error is when there is an effect in the population, so the alternative hypothesis should be supported, but I did not detect it in my sample. So my test estimate was not significant. It was because I couldn't identify it. I either didn't have enough sample size to detect the little bitty effect size, or my particular sample just did not have that effect. So that would be a type 2 error. Now, what does this statistically look like? Well, here we have the distribution of if this is where the test estimate would occur if the null hypothesis was true, and this is where the test estimate would occur if the alternative was present. So if my test estimate came out significant, in other words, it exceeded the critical value, then our decision would be to reject the null hypothesis and support the alternative. However, if the null actually was true, or in other words, the effect being found in the test estimate was only true for my sample and not really true for the population, then we've made a type 1 error. And that's the risk we're willing to take based on setting our alpha level at 0.05. Now, what if the test estimate does not exceed the critical value? What if it occurs over here in the blue area? Well, then we would fail to reject the null. We would retain the null. But what if in reality, in the real population, the effect really was there and it really was true? It's just we missed identifying it in our sample. That would be a type 2 error. All right. Well, that completes our last chapter of the textbook. Congratulations. We went through a lot of null hypothesis significance testing and what that does. We looked at some basic tests, talked about effect sizes and CIs, and some frequently asked questions. Now, if you have more questions, I'd love to see them on the chapter Q&A board. And homework this week is another discussion board item where you help the research methods instructor write his null and alternative hypotheses. And don't forget your last article summary, Art Summary 3. Our final week, our data work week, is going to be running some basic tests and completing your final paper about the research methods instructor's study.